Greetings everyone, and for my friends from the Indian subcontinent, happy Diwali. So before we get into the main presentation, I would like to talk about why we are actually discussing nanoindentation. So in any kind of structural design or when we are developing new materials, these are the few properties that we are most important. So starting with the Young's modulus, hardness, material creep, interfacial adhesion, fracture toughness, compression strength. So if you know all these properties, you really have the full understanding of a material, and then you don't really need to know other things when you're designing, either it's a structural member at any kind of scale, at the MEMS scale, at the automotive scale, or even at the building materials. So so I want you to understand that nanoindentation can perform experiments to measure all these properties, and in some cases just with the same experiments. So this is the power of nanoindentation we are talking about, and this is the main reason why it is getting so much attention these days. So so let's get into the main part of the presentation. Briefly, the outline, I'll go through the history of the nanoindenter that I'm talking about. Then I'll go over the technique part so that we really understand how we are performing these experiments. And then I will mention some of the applications where we have already implemented the nanoindentation technique. We will follow it up with the Q&A session on any kind of technique or application related questions. So we won't spend too much time on this slide. But I wanted to get you an idea that the first nanoindentation in the market came in 1983 by Dr. Warren Oliver, and throughout the last 35 years, it changed few names, and now it's under K. Letancourt. So, for those of you who are familiar with nanoindentation, you will recognize the name of Dr. Warren Oliver. He's referred to as the father of nanoindentation. With that, we have 35 years of expertise in our instruments, and our system has been established as a reputed as a most robust, reliable, and ease of use indenter system. Now, to really understand how this nanoindentation is performed, let's look at this video clip. So we have our sample of interest, and we have our nanoindenter tip mounted on a head. The tip goes and makes contact with the surface. And there could be different kind of tips. In this case, we are using a Berkovich tip. So the tip goes and makes the indent. And while we are doing so, we are measuring the load that we are applying and the displacement that we are getting into the surface. So this is really important. This is all we are measuring, the load and the displacement. And this is our main input during the calculations. Now, another thing is the process is so fast that you can perform hundreds of indents. Like here you see that on a material with different phases, you can perform hundreds of indents to actually figure out at what points in my materials, what are my hardnesses, what my modulus, and all these properties. Now, so now we understand that during the process, what we are measuring is load and displacement. We get this data and we do some post-processing. We apply some contact mechanics, and that helps us understand or calculate the modulus, the hardness, the yield stress, the reduced modulus, and all other properties that I mentioned in my earlier slide. So you have the raw data, and then you are doing actually a post processing of this data based on the properties you are interested in. Now, I don't want you to get scared of this maths, because none of this is done by the user. All you do is select the point on your surface of your sample where you want the indent to be done, and everything else is automated. Everything else, from the performing the experiments to calculating the data, all of it is done automatically. Now, so we mentioned earlier, so we have this nanoindenter tip and it is applying load. So the natural question is, how is this load being applied? And the answer is that the tip is attached to something called actuator, or commonly referred as the indentation head. Those indentation head could be based on different principles. In our case, what we are using is electromagnetic principle. Now, so What electromagnetic principle means is we have a coil and a magnetic assembly here. So you apply a current through this coil and this generates a magnetic force, and that's how you actually are applying the loads on this indenter. And the load basically is going from this shaft, and here's your sample, and the tip indents in the surface. So that gives us our load signal. Now the second most important part was the displacement. So the way we are measuring the displacement is with these capacitive plates. So while this indenter is moving, we are precisely measuring the change in the capacitance, and that's how we know how our displacements are into the surface. So this is a very simple and robust model to measure this both loads and displacement. Now, there are some other ways to perform this measurements, but there are some really problems associated with them. So for example, in our case, we have electromagnetic, so we have linear force control. Our forces are directly proportional to the current we are applying. So if it's a linear system, it's easy to calibrate, and it's very repeatable. Now, in some other cases, such as electrostatic or piezoelectric, what happens is that your forces are not directly related to the current and the responses you're applying. So they are non-linear systems, and the main problem that we see always is that you cannot really calibrate the system to the same reference standard. Now, this is a big problem. When you're performing the measurements, you want to be able to compare your measurements from last month or last year, and also from different instruments. So if you cannot calibrate your system back to the same reference, then you cannot really compare the data. So that's a really big problem with this electrostatic and piezoelectric actuators. But with the electromagnetic, because our load and depth are very independent signals, you can always calibrate to the same reference state. Now, the second most important point during the load is the how much data you are collecting. Now, in our case, we saw that, okay, we have a, let me do this. So we are measuring the load and depth. So you're applying the load on the sample, and at the same time, you're measuring the depth. Now, this is when we zoom on this one specific segment, what we see is that we are not applying one load. We are actually applying two kinds of load. We are applying a mean load, and we are also applying a harmonic oscillations on this tip. Now, what's the benefit of applying these harmonic oscillations? So the benefit is with this signal that we are applying, we get tons of more data compared to the other techniques we discussed. So we get depth dependent data. So while we are actually penetrating into the sample, you are collecting modulus and hardness data at each particular point. So this is really, really powerful. Now, to make it very clear, let's look at these two graphs. So in the left-hand side, you see the data that is collected with the continuous stiffness measurement. And so you're getting modulus and hardness at each depth while you're performing your experiments. It's like less than a minute, you're getting so much data. Now, with some other regular indentation techniques, what you'll get is this just one data point that's given on the right-hand side curve. Now, so this is a really, really important point when you're trying to measure properties on heterogeneous materials or different kind of alloys you are making, different kind of thin films you are making. So if nothing else from the technique part, all I want you to remember is that with the continuous stiffness measurement, you get much higher data, and it's much more valuable when you're doing these nano indentation experiments. Now, to summarize this technique part, the electromagnetic actuation that is independent in force and displacements give you two repeatability of data. The continuous stiffness measurements gives us the depth dependent data on your sample. Now, because of the electromagnetic actuation, we have easy calibrations. You can compare data between different systems and between different time points without having to worry about it. And in the last, the system is ISO 14577 compliance. What it means is that the standards set by ASTM are followed in our systems, and so that's how you can get repeatable data and compare data between different instruments. Now that we know the technique part of nanoindentation, we know how the experiment is performed and what are the main important factors, like why the load is important, why the depth is important. So now let's talk about the application. So who is actually using this technique? Where it is actually utilized in, let's say, today in industries or in the universities. So it has a really broad spectrum of applications, starting from the material science for the regular material processing and characterization to all the way in semiconductor and data storage. On all these data storage devices, nano indentation is being used to characterize these different materials, the new coatings and new processes that are being developed every day. Now, so let's start with the one of the most important one, thin films and coatings. So the problem with the measurements in thin films and coatings is that we want the properties of only the film. So like in this slide, we only want the properties of this red part, but usually what happens is that we are performing the some kind of indentation from the top, and we are measuring properties of both the red and the blue. So we are getting H1 and H2, but what really after is the H1. Now, this is a big problem. You're making a new thin film and you want to know what is the property of my thin film, and you end up measuring the property of the thin film and the substrate. So it doesn't really help you to refine your process. Now, with the nano indentation, you can actually measure the only H1 really, really easy. And this is, again, the powerful superior physics behind our actuator that let us do it. So with our system, what you can measure is the only H1. You calculate the whole hardness and actually remove the substrate effect. Now, and it will become more clear in this data. So in the curve that you see, you'll see that there's a faded out curve, and it looks like the properties are increasing as we are indenting into the surface. But that is not really true. That is artificially inflated properties, because what is happening is while you're indenting deeper into the surface, you are getting the properties of both the film and the substrate. Now, with the nano indentation, we can apply methods. So we call it thin film method, and you can calculate the true thin film properties like you see in the flat part of this curve. So that is something really important while you're measuring all these different kind of thin films, and you want to be really accurate in your measurements. Now, another thing is you can measure on thin films really, really thin. So we are talking about like under 50 nanometers. So even 20 nanometer thin films, you can measure these properties very precisely. Now, the second part associated with the coatings and thin films is their failure. So we are interested in measuring the properties, but we are also interested to know at what point, at what load these films are starting to scratch, at what point they will start to fail. So with the nano indentation, you can perform scratch tests on different locations to measure the failure load of films in a very automated way. So all you need to do is you select a point on your film where you want to do the scratch test, and everything else is automated. So you can very precisely measure at what load my film is starting to delaminate, let's say, or fail. And also at the same time, what you're measuring is the elastic and plastic deformation. So you actually are getting a lot more information than just failure. You are actually measuring the elastic and plastic part of your deformation during this experiment. And of course, like in the right-hand side curve, you can also measure the depth. You can also measure what's my highest depth during the scratch process. Now, moving on, what we have discussed so far are all the ambient experiments. All of these experiments are performed outside in the like normal air. But all these experiments that we have discussed can also be performed inside an SEM chamber. Now, why would you want to do these experiments in SEM chamber? So multiple reasons. The very first reason is in materials such as metamaterials, or commonly referred to as architectured materials, we are trying to understand how the structure is responsible for different kind of properties of this material. At what load my structure is going to collapse, and what load my structure will be able to fully recover. So we are trying to develop like hyper elastic materials. So in this case, you can apply load and you can very, very precisely measure what truss members, let's say if you have a beam structure, you have like a truss structure, you can very precisely measure which truss is failing and what load it is failing. So it's a really, really powerful technique in this scenario. Now let's moving on to the nuclear materials. So we talked in the earlier slides that nano indentation is a fast technique. you can perform hundreds of indents on in a matter of minutes. So why do you need to perform hundreds of indents? So nuclear material is an excellent example of that. So while you're characterizing this material to develop something for the nuclear power plant, so you need to be absolutely sure. You can't just perform 10 data points and do some regression analysis to predict the properties. You want to be absolutely sure that what you are measuring is correct, because these nuclear reactors are designed for 30 years, 40 years. So once they're designed, you can't just have them fail before 30 years. It's a big hazard to the environment itself. So what you do in the nuclear materials is you basically take samples, those are irradiated outside, and on, let's say, 3 samples irradiated at rate 1, rate 2, rate 3, and then you can perform hundreds of indents on each sample, and it precisely tells you until what depth the irradiation had effect and how the properties had changed from one rate of irradiation to the next rate of irradiation. So really useful technique in the nuclear material. Now, another place similar to that is the lithium battery materials research. So nowadays, battery materials are gaining a lot of attention because of their use in even like automotives. There are a lot of electric cars and even the other applications. So the problem here is, how can you increase the performance of the battery? How can you make them last long and have the same capacity, let's say same charge? And the problem is the separators that we have, this lithium material is during the charge and discharge, it expands a lot, and then it contracts, it expands a lot. So it tends to fail during one of these charging and discharging process. Now, so with the lithium, so with the nanoindenter, what we do is we measure the properties of each grain. We can very precisely perform indents on each grain and find out at what level of charge my hardness of this metal is changing. And based on that, we can actually design these batteries much better way, so that we don't have a catastrophic failures during the operation. And a similar kind of material that is gaining some interest these days is the additive manufacturing. So we know in additive manufacturing, we are depositing or we are printing our parts layer by layer. So you print one layer and then you print another layer on the top of it. And so there's a thermal gradient going throughout the your material. So in that case also, we are interested to find out whether my hardness, whether my modulus has changed from my base plate layer to my top layer. So in all these applications, nuclear materials, lithium batteries, and additive manufacturing, you want to perform a lot of indent points, and with the nanoindentation, you can perform this very precisely. Now, so one thing I forgot to mention is, so lithium material is also very environment sensitive. So you can't just perform these experiments in the ambient air. So what you can do is you can actually install the indenter inside a glove box, and so you can perform the experiments on the active materials also without any problem. So we talked about multiple experiments to measure the hardness and modulus in different kind of materials, in battery materials, in nuclear materials, in additive manufactured materials and such. So now let's talk about some more advanced tests, something that are not very useful in some applications, but not everybody is aware of it. And I will show you how nanoindenter can actually be used to perform these tests as well. So the slide here shows you the piezoelectric measurement. So we understand that the piezo materials have mechanical response based on the let's say voltage difference that we applied across this piezo materials. So with the nanoindenter, you can actually measure the directional properties of these piezo materials like S11, S11 and such. So what you do is you load your sample on the sample holder, and the tip makes the contact with the sample, and the other side of the sample is looped through a, let me show it here. So the tip is making contact with the sample, and the whole part is a closed loop. So the sample is a part of the closed loop through the tip. Now what you do is, with our voltage meter, you give it a signal, and based on that signal, the sample responds mechanically. And you can actually measure those mechanical response here. Like here you can see, you can measure, okay, how much depth it went to and such. So based on that, you can actually characterize the piezoelectric materials in a very precise way for your applications. Now, so let's go to the second applications. So here, the polymer characterization. So we understand that polymers are little different than the materials such as metals and such. In metals, we talk about hardness and modulus, but in polymers, we talk about the storage modulus, loss modulus, because these materials are neither fully elastic or fully plastic, so they kind of are somewhere in the middle. And so that's why we call them viscoelastic materials. Now, for the viscoelastic materials characterization, you want to be able to measure the changes in the process, how these polymers are being produced. And to do so, what you need to do is you need to be able to perform a lot of experiments at a lot of different kind of polymers. And perfect example is a tire. So in different kind of vehicles, and you need to have a different tire. They are not all same. And there's a reason behind that, because it needs to be designed based on the, let's say, highest speed the vehicle would go to, or even the weight of the particular vehicle. Now, to design all those tires, you actually have to measure the properties of this tire. You actually have to understand the viscoelastic response of these tires. So you can perform all these experiments using nanoindentation and very precisely map out the properties on different parts of the tire. So moving forward, let's look at this and one example of an array of indents. So as I mentioned earlier, what you can do is you can map out the areas of your material. You don't have to prepare your sample and perform an experiment and get like one indent point, such as like in a regular tensile test. So here what you're doing is you prepare your sample, and it's really easy. What you do is you just have a flat sample, you mount it on your sample holder, and that's it. So 5 minutes your sample is prepared, and then you can go ahead and set up 40 by 40 array of indents. And in this case, so you are talking about 1600 measurements in just 27 minutes. And with this kind of measurements, what you get true analysis of your sample. So this is a two-phase material. So you know how much of my material at what hardness. Is it 50%? Is it 40%? Is it 60%? And then you can design lots of new alloys based on that. So here we are only talking about the surface properties. So moving forward, and this is one of my favorite tests. So you can actually measure the properties into the depth of the sample, not just onto the surface. So this goes back to the continuous stiffness measurement that we mentioned in the starting slides. So with the continuous stiffness measurement, you are measuring the properties through the depth of the signal. You don't really just get one point, you get multiple points throughout the depth. So here we are mapping an area of a sample, and we are also mapping into the depth. So you're getting hardness and modulus into the depth when the sample properties are changing. And on the right hand side, you will see that there's a mapped area of a composite material. You can see the fibers on the top side, they are like going into the surface, and on the bottom side, they are parallel to the surface. So you can map out the properties. It very precisely tells you, okay, how my fiber properties are, where my matrix is, the blue part is the matrix, and it also gives you the properties actually around the interface between the fiber and matrix. So really precise and a great tool to measure these properties. Now, one of the another way nanoindenter is used is for the high temperature experiments. So as material scientists, we understand that if our materials are being used in high temperature applications, such as, let's say, turbine engines or some other kind of applications. Now, to really characterize it, to really understand what my material properties are and how they are changing with the temperature, you should really be doing the experiments at high temperature. So what we allow doing with our nanoindenter is actually you can mount your sample on our high temperature state, and this is a laser heated state. So what's the difference between laser heated and other conventional resistive heater is? The laser heated is very local and very fast. So you can basically cut down the time of the experiment on this experiment. So you can heat your sample as well as the tip. You heat both your sample and the tip, so you have no thermal gradients. Whatever you're measuring is the true properties of the material and at the actual temperature. And you can keep doing the experiment. You can measure your properties 100, 200, 300, 400, and actually see whether my properties, whether my material is like softening or it's remaining the same. The properties are and for different kind of materials. So now, so we discussed many different ways in which nanoindentation is used, and all these examples that you saw are our already users. So they are actually utilizing this nanoindentation in many of these applications. To summarize once again, so the Cayley Tenco nanoindenters are the most reliable and robust and reliable system with 35 years of experience in experimentation and the surface metrology. And these are really easy to use indenters because of the electromagnetic actuation. You can calibrate them to the same reference level each time without any problem. The system is conformance with the ISO 14577, and this is required for the true repeatability of the data. According to the ASTM standards, your system should be ISO 14577 compliance to be able to compare the data between different systems. And the third part, continuous stiffness measurements for the depth-dependent data. Our system is the only system that is able to perform this continuous stiffness measurement because the excellent design of our actuator that is based on the electromagnetic principle. You cannot perform these measurements with other kind of actuation devices.